So in the last lecture we studied about Coulomb's law and coordinate systems. So let's continue further. So what is Coulomb's law? Again, what is the formula? F vector indicating force equal to K Q1 Q2 upon R square AR cap. What is the unit? Units are very important for this course. Newton, capital N, remember. Right? Now what is electric field intensity is? It is nothing but force per unit charge. So it is force per unit charge. So let's say I take this Q2 here. So what will you get? K Q1 upon R square AR cap. Now it is what? Per unit charge. So what will the unit become? Newton per Coulomb. So therefore explicitly I can write in general E vector equal to K. K we know it is 1 by 4 pi epsilon. So 1 by 4 pi epsilon Q by R square AR cap Newtons per Coulomb, or the other unit is volts per meter, because it is also V by L or V by D. And what is epsilon? Epsilon 0, epsilon r. Epsilon is permittivity, epsilon 0 is permittivity of free space, epsilon r is relative permittivity. Similarly, you have something called as mu, which will come further in the subject. So it is mu 0, mu r. Mu 0 is permeability of free space, and mu r is relative permittivity. So this formula is very important for the entire course. So make sure you know this by heart. Okay. So this is about electric field intensity. Then there are some important questions. So electric field due to first infinite line charge. So this derivation is there. Similarly, you have electric field due to infinite surface charge. So these two derivations are there. So in the exams, either this is us, or numericals based on this is us. So 100% these sums will be there. I mean these derivations or numericals based on them. So they will definitely be there. So make sure you understand and do this topic. Don't keep it for option. So let's start with first derivation. Electric field intensity, that is E vector due to infinite line charge. As I said, very important question, derivation of 10 marks. So what is this? It is a line charge, and we have to derive the electric field intensity expression for it. Now since it is a line charge, it resembles a line. So now this line has to be placed somewhere in the space. So if it has to be placed in space, what we require is Cartesian coordinate system. That is why last lecture we studied coordinate systems. So let's assume Cartesian coordinate system as first. So x, y, z using right-handed coordinate system. This is the origin, and let's place it arbitrarily along the z-axis. Now I have placed it along the z-axis. If you want, you can place it along the x or y-axis also. So accordingly, you will get the expression. Everything is fine. And let's assume it has an infinite line charge density of rho L coulombs per meter. C is capital. So now what we have, the unit of charge as coulombs. So now since this is line charge, it will be coulombs per meter. So per meter we have a charge of rho L coulombs. That's what this means. So that's why the unit is coulombs per meter. Similarly, for surface charge, we'll have coulomb per meter square. Per unit area, we have a rho S surface charge. That's what we mean. Now, what is the thing? What is the problem? This is an infinite line charge. Since this is an infinite line charge, we cannot find the expression for E vector directly, because we cannot say anything directly for an infinite expression. But what we know, this electric field vector, E vector, it is what? For a point charge only. Okay? Because force, Coulomb's law is defined only for a point charge. So that's why electric field for a point charge, this is the formula we know. Right? So what we can do, we can find something intermediate as dE vector. So once we have dE vector, we can integrate it over the entire infinite line charge from minus infinity to infinity to get what E vector is. So this is the essence of our derivation, right? So what I have said so far, we have assumed a coordinate system, we have placed it along the z-axis and along the origin. Then what was the next assumption? It has a uniform line charge density of rho L coulomb per meter. So whatever assumptions I am stating should be mentioned in the derivation. These are very important. Again, as I said, this will come for 10 marks. So these sentences will also carry some weightage. Again, you don't have to by heart them. You can just write it in your own words. Okay. Anyways, I'll provide notes, but again I'm stressing on the fact that don't just buy at the notes. Make sure you write it in your own language. Try to understand it and not buy it. So what is the first sentence we'll write? I'm not writing it, I'll just iterate it here. You can find it in the notes. So consider an infinite line charge placed along the z-axis at the along the origin, having a uniform line charge density of rho L coulombs per meter. Second point, since the line charge is infinite in nature, we cannot find the electric field intensity directly. Therefore, we divide it into very small segments. That's what we do for infinite things, right? So we divide it into very small segments, each of length dz, such that dz represents a point charge. Why we representing it as a point charge? Because we know the expression for E vector. Only instead of E vector, we'll write dE vector. So such that dz represents a point charge, let's say dq. So you have seen in derivatives that d indicates very small things. So that's why we are using dz and dq. So what will be the expression for dq? Again, what is the unit for charge? Coulombs. So whatever we write the expression, unit should be coulomb. So let's try to write in terms of rho L. So rho L is what? Coulombs per meter. So if I multiply by meter here, I will get coulombs. So what is that meter? It is dz. So this is the first expression. Coulomb per meter into meter will give coulomb. So we are correct, right? So next, what we intend to do, we intend to find the electric field. So if we have to find the electric field, it will obviously be at some point away from the line charge. So let's say that point is B and it is on the xy plane. Now this is your infinite line charge. So let's say this is the infinite line charge placed along the z-axis pointing towards you. So now electric field, if you observe, for example, this is a mobile tower. How will it go? It will go away from the point charge, right? So if you see, it is somewhat like this, going away. So what is it tracing? It will trace a circle. So it is a cylindrical structure, will be very conducive to solve this problem. So we'll use a cylindrical coordinate system. So I have come from origin to this point. So this is what rho. Now usually I will be like this first. Then I am moving by some angle. So this will be what? Phi. And as I said, I am on the xy plane. So this will be 0. So this is for point B. Similarly for point A, we can write. We have placed along the origin. So x coordinate is 0. Now this is very important. First we are here, then we are moving like this. So again we are here and we are moving like this. So second coordinate for this is also phi and not 0. Then we are some distance above from the origin. So let's say this distance is z. Right? So what we have to find on this point? So we have seen in Coulomb's law, we have to find in this point. So vector will point here. Right? So what we have to find? AB vector. So you know we get r square term. So this distance is r. So for r we require AB vector. So let's find AB vector. It is what? B vector minus A vector. So rho minus 0 will give rho a rho cap minus, if you calculate, it will be z a z cap, because phi will get cancelled. So what will be r? Magnitude of AB vector. So square root of rho square plus z square. Then what do we require? AR cap also. AR cap will be what? AB vector. So rho a rho cap minus z a z cap upon magnitude of AB vector rho square plus z square. So what we can write? Therefore the electric field intensity dE vector is given by 1 by 4 pi epsilon dq by r square AR cap. So therefore dE vector equal to 1 upon 4 pi epsilon. What is dq? Rho L dz. So rho L dz upon this is r square. So what is r square? Rho square plus z square. Rho square plus z square. What is AR cap? This thing. So rho a rho cap minus z a z cap upon square root of rho square plus z square. So I can write this as 3 by 2. So this is raised to 1 by 2 and 2. 2 plus 1 by 2 is 3 by 2. Yeah, right? So next step. Now we can make use of symmetry. So what is this? This is we are using as a cylindrical coordinate system. So since this I have this vector like this, since this is infinite line charge, so for every positive point I'll have a negative point. So let's say this is a negative point. So I'll find the electric field intensity from this also like this, right? So this is coming like this. So if I resolve, it will be like this. So this is minus z and this is rho. If I resolve this, this is plus z, this is rho. So rho we are getting here and z are in opposite direction. So it will get what? Cancelled. Right? So what we can say, by use of symmetry, you can just write one sentence. By use of symmetry, we can say that a z cap gets cancelled. So what will be dE vector? So therefore dE vector simplified expression will be 1 upon 4 pi epsilon rho L dz upon rho square plus z square raised to 3 by 2 into rho a rho cap. That's it. Okay. So now we have the expression. So now we can integrate it. Therefore the total electric field intensity E vector is equal to integral. We are going from minus infinity to plus infinity. dE vector. So what is dE vector? So I'll write dE vector. So this is dE vector. So therefore E vector equal to, what will be constant? This will be constant, 1 by 4 pi epsilon. Next rho L and rho will be constant, rho L and rho, because dz is the variable. So integral minus infinity to infinity dz upon rho square plus z square raised to 3 by 2 a rho cap. So we have to just solve this integral and we will get our answer. Therefore E vector equal to rho L into rho upon 4 pi epsilon. So we can first solve this integral, right? So what we have to do? We have to solve this integral. So what will be simple? What substitution will be simple? In fact, this is what rho square plus z square, right? So if you think that we substitute z is rho tan theta, so what will be rho square plus z square? So it will be rho square plus rho square tan square theta. So rho square times 1 plus tan square theta. So rho square secant square theta, right? So we can use this substitution. So what will be dz then? So therefore dz equal to rho into derivative of tan theta is secant square theta d theta, right? So we can use this thing. So therefore let's say the integral is I. In the exam you write stepwise. I equal to integral, and then what will happen? The limits will change, right? So what will be? So we'll have limits of theta, right? So tan theta is z by rho. So when z equal to infinity, what will be theta? Z is infinity. So tan theta is infinity. So for this, theta is what? Tan pi by 2 is infinity. So theta is pi by 2. Then z is equal to minus infinity. So theta will be what? Minus pi by 2, because tan of minus theta is tan theta. So this will be minus pi by 2. So integral minus pi by 2 to pi by 2 dz is rho secant square theta d theta, right? Upon rho square plus z square is, we got it as rho square secant square theta. Yeah, that's it. And arrow cap. Okay, arrow cap is not there. We are just writing integral. So what will cancel? This rho will cancel with this square, and this secant square theta will get cancelled. So therefore, so 1 by rho becomes constant. So 1 by rho integral minus pi by 2 to pi by 2 only d theta. Correct? So integral of d theta is theta from pi by 2 to pi by 2. So this will be pi by rho. Right? So substitute it over here. Pi by 2 minus of minus pi by 2 is pi. Yeah. Right? Okay. So it should not be pi by rho. We have made some mistake. dz upon rho square plus z square raised to 3 by 2. Okay, this should be raised to 3 by 2. So it will get cancelled with this square. So we'll get cube. So this will be, I'll write it again. I equal to integral minus pi by 2 to pi by 2 rho secant square theta d theta upon rho square secant square theta, right? rho square plus z square is rho square secant square theta raised to 3 by 2. So therefore I equal to integral minus pi by 2 to pi by 2 rho secant square theta d theta upon this square will get cancelled with this 2. So rho cube secant cube theta, right? So now this will cancel with this, 2 is remaining, this will cancel with this, 1 is remaining. So I is integral minus pi by 2 to pi by 2 1 upon rho square into 1 upon secant theta. So cos theta d theta, right? So therefore I equal to 1 by rho square is constant, integral of cos is sin theta, right? Between the limits minus pi by 2 to pi by 2, right? So sin pi by 2 minus of minus sin pi by 2. Sin pi, so 1 by rho square into 1 minus of minus sin pi by 2 is minus 1. So it is 2 by rho square, right? So now we have this integral. So therefore E vector equal to rho L into rho upon 4 pi epsilon into what was it? 2 by rho square. So 2 into 2 pi gives 4 pi. So therefore, and we have this arrow cap, remember, it is a vector. So therefore E vector equal to, and this row will get cancelled with this row. So rho L by 2 pi epsilon rho arrow cap. So this is what is the required expression. Unit is volts per meter, or if you want you can take newtons per coulomb. Okay. So this is the way we have to solve. So similarly on these lines we have surface charge. Okay. So let's solve that. So I will not solve that completely. So you solve it yourself. I will tell you the concept. So electric field due to infinite surface charge. So again we have to place the surface charge somewhere, right? So let's say we place it along the xy plane. So this is x, y, z. So I have placed it along the xy plane with green pen, right? So again what we did for infinite line charge, we assume the uniform current line charge density as rho L. So here we will assume the uniform surface density as rho S coulomb per meter square. Then what we assumed, since the line charge was infinite in nature, we divided it into very small segments, each of length dz. Now that was length, so we use dz. This is surface, so what will we use? ds. Yes. So since the surface charge is infinite in nature, we divide the surface charge into very small surfaces, each of surface dz, right? So this is my ds, right? Then what will we say? Such that each surface represents, what will it represent? Again a charge, point charge. So it is, the surface is so small such that it represents a point charge. So we will get dq equal to, instead of rho L dl, what will we get? Rho S ds, coulomb per meter square into meter square. So this will be our first equation, right? Then what will we say? We have to find for this surface charge electric field intensity somewhere. So let's say on the z axis itself. So let's say this is point A. So what will this be? Rho phi 0, like previous thing, and this is point B. So what will this be? Again 0 phi z, right? So what will we write? So the vector is this vector. So what vector we want? AB vector. So we will find AB vector. Again I will not solve this, so I will just write it directly. So minus rho arrow cap plus z az cap. So what is the difference? Instead of plus minus, you are getting minus plus as compared to line charge. Then you will find r is magnitude of AB vector. Then you will find AR cap. Then you will say d vector, since it is a point charge, is 1 upon 4 pi epsilon d cube by r square AR cap. So we'll substitute here, right? So then what you have to do? Then you have to make use of symmetry. So since you have ds here, diametrically opposite point, you will have another ds prime, let's say here ds dash. So it will come like this. So if you resolve this 2, so this will be plus z. Where will this go? In, again we are using cylindrical coordinate system, so this will be rho. So this will be again z, this will be rho. So in this case, what is getting cancelled? Rho, arrow cap. So this arrow cap will get cancelled in this expression. So you can just write one sentence: by making use of symmetry, we see that the arrow cap vector unit vector gets cancelled. So we discarded that. So therefore d vector is just az cap wala expression. Then you integrate from what? So then you integrate to get e vector, integrate d vector from minus infinity to plus infinity to get e vector. Fine. So then that will be what? E vector due to surface charge. Okay. And we'll get that as rho s by 2 epsilon az cap. So that will be your e vector for surface charge. Okay. So this will be for your assignment. Okay. So after the assignment only, I'll upload the notes. So let's see. Okay, I'll upload line charge derivation, but I'll not upload surface charge derivation. That you have to take help from line charge derivation and then you have to derive. Okay. So we'll stop here. Next lecture we'll solve numericals.